Let's talk about the force between particles. So last video we talked about how you could shock your friends and stick a balloon to walls. And now we're actually going to talk about why this happens. If you're going to hold something there, it's got to feel a force. And these charged particles feel forces. So this guy named Coulomb, who we'll meet in a minute, well, we can't really meet him because he's long gone. But anyway, we're going to talk about his discovery. Sorry if I got your hopes up about meeting him. And just like in class, here are the big ideas, the things you need to take notes on and understand. Take a moment and write these down. Now let's get on with the show. So our journey begins here in 1784 with French scientist Charles Augustin de Coulomb. That's this guy, right here. Now, he wanted to measure the force and find out a rule for the force of attraction or repulsion between charged particles. And to do so, he used this torsion balance. I found this little picture of it and I thought it was pretty neat. So the gist is that you charge these spheres, you hold a little charge next to it, and a torsion balance works in that it spins. So this will spin a little bit. And because the force was so small, or if you measured it, it was big, just by this thing rotating, you could be able to figure out really small quantities, or were able to figure out really small quantities. Let's talk about some of the things Coulomb found out. First of all, what happens to the force between charges if they get farther apart? When you rub the balloon on your head, does it instantly go towards the wall, or do you have to get pretty close? How about if you want to pick up something with electric charge, not like physically pick up something? Coulomb found out that it goes as 1 over r squared, where r is the distance between the particles. Next, he found out, well, what happens if you increase the charge? Well, he found that it is proportional to the product of Q1 and Q2. We use Q for charge. I don't know why, it just is. So you use Q for charge. Wait a minute. This is shaping up a lot like gravity. But here's the difference. F is attracted if the charges have opposite signs, which is something different than gravity. Because when we talked about Newtonian gravitation, all it says is things attract each other. But now, they don't have to. So because force is a vector, we add this little r hat. And which way does it go? Well, we define r as a position vector. And it points, we'll say it points to the other charge. So if we were looking at the position from r, let's call this r1 to 2, it points from charge 1 to charge 2. Right, so it always points away. And I'm going to put an E on charge because that's how spelling works. Now let's put all of these together and start talking about what we can do with it. So let's put all this together. We have the force is proportional to Q1, Q2 over r from 1 to 2 squared, our vector pointing from 1 to 2, this negative sign up here, because what happens? If the signs are opposite, they attract. So that negative is because opposites attract. And since this points from 1 to 2, this little r vector points from 1 to 2, this negative means that if this is positive, this is negative, it will attract. In other words, this negative charge and this positive charge will feel a force of attraction. This would be the force of 2 on 1, or 1 felt by 2, however you want to label it. But the important thing is it's negative, so it'll be attracted. The only thing we're missing here is how are these exactly related? Because if you've been doing dimensional analysis, you would say that Coulomb times Coulomb divided by distance does not equal force, which is newtons. So we are missing a constant K, Coulomb's constant. So what K is, this is about 9 times 10 to the 9th. I told you the constant was bigger than gravity. This is about, well, what, 11 to 9, 20 orders of magnitude bigger than the gravitational constant. Newtons per Coulomb squared, meter squared. Another way that you'll see this sometimes written is 1 over 4 pi That's a horrible pi. Let me redo that. 1 over 4 pi epsilon naught, where epsilon naught is a constant. It is the permeability of free space, and we will get there later. So let's talk about a little conceptual example right now. We have two charges, a 1 nanocoulomb. Remember when I said coulombs are really big? So most of things are going to be measured in nano or micro. Nano, just by the way, nano equals 10 to the minus 9. It's a metric prefix. So let's look at a couple questions. First, which charge 1, it's got 1 nanocoulomb, charge 1, or charge 2, feels a larger force? Okay. What is the direction of the force on each charge? Now, after looking at this, hopefully you've said, oh look, they have the same sign, which means the force goes this way. So this would be the force of 1 on 2, and this would be the force of 2 on 1. And hopefully for the magnitude, what do you know? What are these? You've got a force, 1 pushes on 2, the reaction force, 2 pushes on 1. It's a Newton's law force pair. So now let's use Coulomb's law to find the magnitude of the force on each charge. So we're going to start with Coulomb's law right here, and now we just plug in numbers. And by the way, now you know that the magnitude of F2 on 1 equals the magnitude of F1 on 2. So let's look at the force on the 1 nanocoulomb charge right now. So let's find this force. All right. So if we're plugging in our numbers, we would say that F is equal to negative, because we've got to get that direction right, Q1, Q2, R hat. Now R hat, whenever you see this little thing that's a caret, this means it is a unit vector. So it is a magnitude of R hat, magnitude, equals 1. All that little arrow does, that little caret, it just points the direction over r squared. Now let's plug in some numbers. We'll say 9 times 10 to the 9th. That's the constant. 1 times 10 to the minus 9 times 1, or 2, sorry, that's the other charge, times 10 to the minus 9. All over, what's the distance? It was 0.05 meters. All that gets squared. Don't forget the minus sign. That is really easy to do. And the minus sign just says this is positive, this points this way, so this is r hat, points that way, and the minus says it's not going that way because they're repelling. And you'll plug this into your calculator, those cancel. They don't really cancel, but when you multiply 10 to the minus 9 and 10 to the 9th, you get, well, 10 to the 0, which is 1. All right, and you just plug that in your calculator and get an answer with the direction. But what happens if you have multiple charges? This is where we're going to use this principle called superposition. It's like normal position, but has been bitten by a radioactive spider. That is a lie. All superposition means is that you add all forces. All right. So you have multiple, you just add them up. So if I'm looking at the force on, say, this charge, well, it's going to be attracted to this one. I'm going to call this F13. It's going to be attracted to this one. This is F1. I'm going to label this one 2. I'm going to label this one 3. And then the resultant vector of these is going to be somewhere, well, if we add these together, so we'll transfer this one over here, the resultant vector is going to be this way. And that's going to be your total force. All right, pulling in some angle. Also, very important, whenever you are doing this, your R, in this case, R from 1 to 3 is this distance. So it would actually be 5 centimeters using Pythagorean theorem. Always, always, always use the distance from this charge to whatever charge you are looking at. Now, I've worked this out in another video, And the next video in the sequence, goes through a lot of different examples using Coulomb's law. So I'd like you to go take a look at that. That way you can see some problems in action, see some progress on them. And if you have any questions, just shoot me an email or ask. Hope this was helpful, and I will see you later.